Greetings, everyone. I'm Jinghan Jia from Michigan State University. I would like to express my gratitude for your presence at this paper presentation. I'm thrilled to present our latest research on robustness-preserving lifelong learning through dataset condensation. To start, let me introduce the key components and provide some background information of this paper. One important aspect of this paper is the concept of class incremental learning. Traditionally, tasks with fixed class numbers are referred to as static learning, where the training data and class numbers are predefined. In contrast, class increment learning deals with an unknown data stream, where the class number increases as new tasks are introduced, as illustrated in this figure. The primary difference between the class increment learning and static learning lies in their training goals. Specifically, class increment learning requires not only learning new knowledge as new data and classes emerge, but also retaining old knowledge as much as possible and preventing forgetting. There has been some work studying class increment learning, but very rarely studies robust class incremental learning. The idea of the adversarial robustness is the basic topic in the deep learning area, and here I would like to briefly repeat it. How to generate such a tag is that we maximize the training loss. The idea of the training is to equip the model with the robustness against adversarial attacks during the training. The adversarial training can be formulated into such min-max formulation. Specifically, during training, we first need to generate adversarial examples given the current task, which corresponds to the maximization problem. Then, the model is trained to minimize the training loss on the adversary examples, which can be viewed as the worst-case loss, so that the model will naturally gain robustness after it is trained. Regarding the topic of robustness of their class incremental learning, there are two challenges to consider. The first challenge involves the lack of principles for memory replaying, which refers to determining which data should be stored in the class incremental learning. And the second challenge pertains to decreasing the retraining robustness over time on old classes. As demonstrated in this figure, to address these challenges and develop a robustness of their class incremental learning approach, we propose a new framework. Here is one overview of our proposed framework. So the key idea of our method is that we leverage memory replaying methods based on the cosine selection and the robustness training to fulfill the data-efficient robustness-preserving class incremental learning. As we can see from this figure, we will keep a small ratio from the original training dataset and conducting memory replaying via those cosines and robust training to retain the good robustness on the past tasks and the current task. One key technique in this paper is that we make the cosine selection via bilevel optimization. The cosine selection can be formulated as a bilevel optimization problem shown below. The lower level is finding the best model by given a cosine W. The upper level is finding the best cosine given the model theta star W. The selection variable is the W, and there are some constraints on W. So each element of W should be 0 or 1, and the sum of W it should be equal n, and n is the size of the cosine. To solve this bilevel optimization problem, we adapt convex relaxation on W. And in this case, we can directly use the standard bilevel solver in deep learning, like a grand unrolling, to solve this bilevel optimization problem. Next, we illustrate how to integrate the select code set ST to achieve a data-efficient robustness-preserving class incremental learning. Here we propose a new loss function to fulfill this. As shown below, this function can be divided into two parts. The first part of this loss function is traditional adversarial training loss, which learn robust knowledge on the current task at the stage T. And the second term is the regularization term, which return the previous learned knowledge from theta t-1 via the code site of the past tasks. By combining these two terms, we can fulfill the data-efficient robustness-preserving class incremental learning. To demonstrate the effectiveness of our proposed method, we conducted experiments on the Civatin dataset. We compared with two baselines. The first one is the random data selection, and the second one is the influence score-based method proposed in this paper. And there are two evaluation metrics we report in this paper. The first one is the standard accuracy, and the second one is the robust accuracy. Here are the main results. Let us see the left table first. Each row in this table represents the performance of the model at a different stage during class incremental learning. We report the accuracy on the different tasks separately. The first conclusion is that our proposed method outperforms the baselines over time-evolving tasks. The second conclusion is that our method achieves the best standard accuracy and a robust accuracy at current task, which is shown in the diagonal of this table. Besides, we also do the application study about how code set size influences our method and other baselines. In this figure, we can see that the robust accuracy will increase with the code set selection size growing on all methods. And we also can find that our method yields most significant improvement in low data regimes. In summary, in this paper, first we found that adversarial robustness could be forgotten over time for class incremental learning. Secondly, we propose code set selection plus adversarial training to preserving robustness of class incremental learning with data efficiency. Third, we found that the improvement over baselines becomes more significant in low data regime. That's all for my presentation. Thank you for your presence again.